Good day everyone, I'm Shaina Ashley Abrasado, and in this video, we are going to tackle on solving static equilibrium problems. Here is our lesson outline. First, what is static equilibrium? Second, the conditions for static equilibrium, and lastly, solving static equilibrium problems. So what is static equilibrium? Static equilibrium is a state where an object is at rest and the net force acting on it is zero. This means that the sum of all forces acting on the object is balanced, resulting in no acceleration or movement. Here are examples of static equilibrium. Book on a table. The force of gravity pulls the book downward, and the normal force exerted by the table balances the gravitational force. As long as the book is not accelerating vertically, it is in static equilibrium. Another example is a chandelier hanging from a ceiling. The chandelier is held up by a chain. Its weight, the force of gravity pulling it down, is counteracted by the tension force in the chain, which pulls upward. Since these forces are equal and opposite, the chandelier remains suspended without moving. Conditions for static equilibrium. For an object to be in static equilibrium, two conditions has to be fulfilled, that is, translational equilibrium and rotational equilibrium. These conditions make sure that the object is not experiencing any linear or angular acceleration, meaning it is at rest or moving with a constant velocity. Static equilibrium requires two conditions: no net force, sum of all forces is zero, and no net torque, sum of all torques is zero. To sum up static equilibrium, the translational velocity and the rotational velocity should be equal to zero, and the downward force is equal to upward force for it to be balanced, as well as the net force and acceleration must be zero for it to be called static equilibrium. So now let's try and solve static equilibrium problems. Problem 1. A 10 kg box is supported by a wall and the floor. Find the normal forces Nx and Ny exerted by the wall and floor. So the given mass is 10 kg and the weight is equal to mg, which is 10 kg times acceleration due to gravity, which is 9.8 meters squared. And so the other side, we all know that fx should be equal to 0, as well as fy, which is torque, is equal to 0. So here is the solution. So Ny is equals to force weight equals mg, which is we multiply the mass of the box 10 kg multiplied by acceleration due to gravity 9.8 meter per second squared equals 98 newton, and the nx, which is the wall, since the net horizontal force is 0 and x is 0. And the final answer is the normal force exerted by the wall and x is 0 n, and the normal force exerted by the floor Ny is 98 n. Problem number 2. A 40 kg child sits on a seesaw 3 meters away from the pivot point. The mass of the bar is 10 kg. Where should the 30 kg child sit to balance the seesaw? What is the normal force exerted by the pivot point? On the free body diagram, the child on the left is 3 meters away from the pivot point, and the child is exerting a weight force called F1. And on the other side, the second child is x meter away from the pivot point, which what we are looking for, and the child is exerting a weight force called F2. And the mass of the bar also has a weight force, and the pivot point also have normal force, which is an upward force. And now let's start calculating for the normal force. The sum of all forces in y direction must be equal to 0, and now the normal force is a upward force, while the other three are downward forces, which is the F1, F2, and the weight force. That's why we put negative sign on it, and now we move it to the other side of the equation, and it will become F1 plus F2 plus the wave force of the bar is equals to the normal force exerted by the pivot point. So the first child's wave force is mg, so we have to multiply it to acceleration due to gravity, which is 9.8 meter per second squared. So that is 40 multiplied by 9.8 meter per second squared plus 30 multiplied by 9.8 meter per second squared plus 10 multiplied by 9.8 meter second squared equal to normal force. And we add them all up, it will equal to 784 Newton. Now that we have the normal force, let's calculate the location on where the 30 kilogram child should sit. So now let's choose the center of rotation as the pivot point. Therefore, the normal force and weight force will not create a torque because they are equal to 0, so there will be two torques created. On the left side, there will be a counterclockwise torque, which is T1, that is positive, and on the other side, T2, clockwise direction, and it is negative. So the sum of torques must add up to 0, so that is T1 minus T2. So if we move T2 on the other side, it will become T2 is equals to T1. So that is F2 times R2, which is F2 times X equals T1, that is F1 times R1, that is F1 times 3 meters, and F2 is M2G, and F1 is M1G. So the second child's weight is 30 times X equals 40 times 3 over 30, so we are going to cancel 30, and we are going to cancel 0, so that is basically 4 over 3, so that is 4 times 3 over 3, and we are going to cancel 3, so therefore X is equal to 4 meters. So here is the final answer. Therefore, the child should sit 4 meters away to balance the seesaw. And that is all. Thank you for watching.